Hello. Getting everything sorted. Welcome. I am live. So are you. So are we all. Today, Basic Math 101, first video, so there's probably going to be a lot more wrong than there will be right. Please be patient with me. So far as in, where we're starting is from the very beginning, because I don't imagine a lot of people, especially right now, oh, there we go. Well, this is very confusing to me. It's backwards. Oh no, this is not going to be good. It'll be fine. Oh, much better, much better. I know. Give me 5 more minutes to situate. So, as it is the middle of June, and not a lot of people are interested in academics at the moment, just trying to get through their summer in peace, I will be starting off with some of the very, very basic math stuffs. That is to say, from decimal place system, addition, subtraction, rounding, estimating, which is a very big and necessary topic, to be honest. That fits in between multiplication, division, exponential notation, and the order of operations, and solving geometric applications with the thereof above information. Going forward, currently, I'll keep you posted if I change texts, but I'll be going through the Basic Mathematical Skills with Geometry, which is the 6th edition, written by Hutchinson, Bergman, and Barato. The idea behind these videos is to perform more of a math lab. To perform more of a math lab, giving people opportunity to ask questions. Be like, hey, I know you're talking about this, but can you answer questions about my algebra homework? It's like, sure, please hit me up. I will try to answer your question as best I can. But without a volume of people doing that, we'll just go over topics such as these in about the order of importance. So basics first. Then after this, we'll probably graduate into some very basic algebra. And then from there, some very basic geometry, and then probably trigonometry, and calculus, and so on and so forth. With that, let us get started with today. The entirety of chapter 1 from this book will probably be covered today. I am hoping that as you have access to YouTube in general, you know the basics of addition, subtraction, multiplication, and division. You may not know like a lot of tips and tricks, or you may not care for it. That's fine. That is why we're here, isn't it? Okay, so starting off with our decimal value place system. We will have... So the decimal value place system makes the difference between a $1 bill and a $10 bill. It is all the matter of where that zero is. If you had a decimal here, that is going to generally be greater than if you had the decimal here. And as place values go with words, exactly, we have, the ones place, the tens place, and eventually the thousands place, the 10,000s place. And once we get into the thousands and 10,000s, we put a comma just for visual context so that... Sorry, I was checking something. Okay, sorry, just for visual context, to kind of know where things are. In some other languages I have noticed is when they put, instead of the comma, they put a dot. Now that's doable, but as long as you know where the system goes. It just kind of gives you a visual context of where and how things are. So as far as placement, we're going to go 1, 2. You'll be familiar with this particular system. It is what we use for most everyday items. These are our basic counting numbers. They are digits, and the reason why there are 10 digits is because we have 10 digits. If we had more, we would have more. If we had less, we would have less. Now, as far as placement, assuming the decimal place is here, this would be the ones place, the tens place, the hundreds, the thousands, comma there, 10,000s, 100,000s, millions, 10 millions, 100 millions, and billions. And this does go and get bigger because then you'd have 10 billion, 100 billion, etc. You'd also have trillions, which we don't necessarily mess with that on a personal basis. That's more of a government debt thing, which that's a whole nother topic. So as far as we generally will be concerned in general maths, that'd be probably situated more in the 100,000s. Arguably they have more than 26 because of the keyboard, but albeit we have binary, which are the digits for the computer. Arguably there are computer systems which handle negative ones, zeros, and ones as opposed to being just binary. As far as computer fingers, I don't know. Very good question. I will keep that for later. I will get back to you next time. Let's see. Digits, place values. So a quick thing, usually done in some elementary contexts, is to write a number in what's called expanded form to help kind of give the gist of what numbers are where. So for an example, we have number 456, and we are to write it in expanded form. This is just highlighting the place values therein. If you have homework that asks for this, it'll be written as such. So expanded form is where you have the 4 times its place value, which would be the ones, tens, 100s place, plus 5 times its place value, which was in the tens place, plus 6 times its place value. So that is expanded form. And this is just to help illustrate to us, the viewer, more in depth of what is where and how much is the value. I think there's not much to go into, but as far as decimal value systems, it makes the difference of like where the decimal is and how to write it in expanded form when asked. The most important thing I have seen as far as being able to understand decimal values is when you're writing a check. So you'll have some sort of check. It's from you to whom, and then you have like 168.25 because whatever you're paying for, you'll have to write it in words before you sign off on it. So this bit, we're going to use 168.25 as our example to write it in words. So you simply put 168, and the and is very important because it indicates where the decimal point is. So in writing this, you would have 100. Assuming I spell correctly. I did major in math, not English, so bear with me. And 25. So that is what you would write on your check where you need to write it out. And as a part of a check, you tend to write in cursive, but that's also another detail for another time. So you get 168, 35. If you were to say have a number, let's see. 103,000. And you see how verbally just put and in places. Mathematically, let's say you're talking to a computer about numbers, that computer is going to say you have decimal places everywhere. So just because you speak it a certain way doesn't mean you write it that certain way. English is lovingly difficult that way. So we have 103,900. Hi. And one more example, just for giggles, because there aren't enough of them. So, the particular number having a digit in every place that is not a non-zero. So we have 20, 1,000, 800, 12. And that should do. So yeah, that pretty much covers the when, where, how, and why of decimal places, writing in numbers. This is probably the most important. Second to knowing that different values have, or different places have different values, of what you can take away from decimal places. Comments, questions, concerns? Alrighty. So, as that was for decimal placement, we next have, let's scooch things over. Ooh, that's much better. We have additions. The idea of addition. Very simple. You take two numbers and put them together, right? So if you had 1, 2, 3, 4, 5 sticks, and 1, 2, 3, 4, 5, 6, 7, 8 sticks, and you were to add them together, 5 and 8, be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 sticks. That is the basic gist of addition. A great notation is that adding things are putting together items that are alike. So like these happen to be sticks or tally marks, into which we have the same thing, and we can add those. But if you were to have 1, 2, 3 circles and 4 X's, you cannot necessarily add these unless you were to put them under some same category saying, oh, tic-tac-toe symbols, in which case you have 1, 2, 3, 4, 5, 6, 7. But otherwise, they would just be 3 circles plus 4 x's, and that would be your answer because they don't combine. Reading the comment. A Googleplex. Okay, so I'm familiar with the Googleplex, but I forgot its meaning. Yeah, this is true. That's kind of funny. So it goes back to how this takes so long to write, and we can just simply symbolize it with a number. And then there are other words or symbols that illustrate a much larger number, kind of like how pi, if I may, equals 3.1415. And that keeps going for the ever and ever. There are a lot of digits to that. It's much more simpler to write pi. Yeah, it's kind of funny. Math gets small and big at the same time. So the general gist for adding is putting two like things together. So if we were to add like 8 and 9, it would be, 17, just because we know inherently 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 5 and 5, that's 10. Numbers. 3 and 4, 7. So that equals 17. So a great example of these. Now, there are two ways I have often found to add numbers. Personally, I add from left to right because in situations where you're having to do mental math, it makes a lot more sense to get the hundreds place right before you get the ones place right. If you're trying to estimate what your monthly bill is going to be, you're wanting to get closer in the hundreds than you do in the ones. But I know a lot of textbooks add from right to left. So if we're adding from left to right, that's 3 and 5, that's 8, 5 and 4 is 9, 2 and 6 is 8. So that comes together real nicely. And working in the other way, you still get 2 and 6 is 8, 5 and 4 is 9, 3 and 5 is 8. So it comes out to be the same. The approach is whatever feels best for you. I know that's not how it's often taught. You are taught to do a way, you have to learn that way. Math should feel good to do. If it doesn't, that's probably because you can do it a different way that feels better. That's my biggest pet peeve about like general math being taught. Let's see, another example. Let's say we have example 43 increased, because increased also means to add by 25. So from left to right, we get 6 and 8. But if we were to add, and you can swap these because we will visit y in a moment, you get 5 and 3 is 8, and 2 and 4 is 6. Et voila. And the reason you can swap these is because the way in which several whole numbers are grouped does not affect the final sum when they are added. So this is verbatim the associative property of addition. What that means is, let's say we have 6 plus 3 plus 2. And if you were to sum these, because 6 plus 3 plus 2, we were to sum these first. So 6 and 3 would be 9 plus 2. 9 and 2 is 11. But if you were to do it the second way, they would come out to be the same. So in addition, order does not necessarily matter. just so that you may be able to read it. This is and yes, I have a book open because I cannot spell it from memory. So, and I'm going to use letters because often letters are used to represent numbers in mathematics to display the idea of something. So if A plus B plus C is the same A plus B plus C, if you're going over the topic of addition, this will probably be on a test because they want you to know the name of important properties when it comes to mathematics. It's very important. And another smaller, no less important rule is called the additive identity property. So what that means, the additive is when the sum of 0 and any whole number, or any integer to be, any number, just any number. I don't know why they had a modifier for that. So the sum of 0 and any number is just that number. So that means, in the example of 0 plus sum 233, we don't add anything. So there are 233 tally marks, and we don't add anything to it. So there's still 233 tally marks. 0 and 4, 5 and 0. So we have 1, 2, 3, 4, 5. So the answer would be 5 and 4. 1, 2, 3, 4. And we have 4. So that means 0 plus any number equals that number. Again, if you were to have a test over the properties of addition, it would include these guys. These guys, very important. And as you get into the thick of it in bigger math, these will just be understood to be true as you keep going. I have run out of paper. So then, as far as word problems go for mathematics, let me take that away. What you'll see in a lot of word problems are applications. So we have add, which indicates to add two numbers. So if you were to add 25 and 33, that would just be 25 plus 33. 2 and 3 is 5, 8. Yes. But add can also look like more than or increased by. Plus. I'm pretty sure this one's not going to be used very often, but it's there. So phrases such as 36 increased by 12, it still means 36 plus 12. So 3, 1 is 4, 6, 2 is 8. Or if you get 8 more than 10, you get 10 increased plus added to 8, which would be 18, and so on. So the verbiage can change. As long as you understand that you're putting two things together, that is the idea. So, a funny topic that keeps coming up with addition that I've seen is like, so far we've had things that added that didn't necessarily have something called carry. Let's see. So we have this number, and we have an example of 58 plus 36. Specifically, carry has to do with when you have 8 plus 6, and we're starting from right to left. 8 and 6 is 14. Well, where does this 1 go? It can't go into the 1's place. It is a teen. It is a 10. The 1 goes into the 10's place. So you carry the 1. So instead of being dropped down here, it goes and sits atop the 10's place, so that when you add the 10's, you make sure to remember to add that 1. So 5 and 3 is 8, plus 1 is 9, is 94. Now this is very important, especially if you stack your numbers to add them. Let's say we have 256 plus 100, well, not 100, sorry, 18. It is important to get your placements lined up, and the best way to do this is get the decimal spot in the same column. So then we get 6 and 8 is 14. There's that 10. So it goes over 1, 5, 6, 7, and 2, 274. Now to do the same thing, but from left to right. And this is where a lot of people get upset, because it's kind of funny. So you get your 5 and 3 and your 8, but you get your 8 and your 6 and your 14. So you have to scratch out what you just did. But you got closer to understanding where your answer was going to end up from left to right than you did from right to left. It is also a personal preference of mine. You do you, as long as it's correct. It's the best way I can explain it. So then we have 256 and 18 going from left to right, so we still drop that 2, 5, and 1 is 6. 6 and 8 is 14, so that changes to 7, so 2 is 74. Yep. And then, because numbers do not tend to be added just 2 at a time, we get stuff like several at a time. Let's say 3, 6, 7, 8, 2, 5, 9, 2, 7, 2, 3, 5, 6. So we have 3,678, 259, 27, 2,356. Now, laugh at me if you will, we will go left to right. So 3 and 2 is 5, 6 and 2 is 8, 9, 10, 11, carry the 1. 7 and 5 is 12, 13, 14, 19, carry the 1, that's a 2. So 8, 9 is 17. 17 and 7 is 24, 30. So 0, carry the 3, so 9 and 3 is 12. So you have a 2, carry the 1 again. And 1 and 2 is 3. So you should have 6, 3, 2, 0. And for ease of mind, we will also do it from right to left. And this is also me personally checking my answer, because if you've ever done any sort of math, you can get an uneasy feeling with maybe being right, even if you have done math all of your life. So 8 and 9, that's 17, and 7 is 24, 24 and 6 is 30, carry the 3, 3 and 7 is 10, and 5 is 15, 17, 17 and 15 is 23, carry the 2, 2 plus 6 is 8, 8 plus 2 is 10, 3 is 13, oh no, oh no, I don't see it correcting. See, this is why we check our answers. Right? If you do it from right to left, you should try it left to right. Oh boy. So 2, 4, 10, 13, carry the 1. 1 plus 3 is 4, 5, 6. So these bits were right. Why was this one wrong? So the reason why checking our answers is so important is because sometimes we just are wrong. We get wrong. We be wrong. So one more time, from the left to the right, just for comfort, just personal comfort. So 3 and 2 is 5. 6 and 3 is 9, 10, 11. 5 and 10, if you can add things easier, like 5 and 5 is 10, that's super easy. So that's 19. So it turns into a 2. 8, 9, 17, 24, 30. So 9, 10, 11, 12. That didn't make any sense. Because that's 10. No, that is right. Okay. So yeah, that's still 2. So that's 12, and you carry the 1 onto 3. And voila, you have 6, 3, 2, 0. So this arguably is correct because we've achieved it twice. In this we have achieved once. So that means this application was wrong. So we will try this application one more time. "17, 24, 30, 10, 15, 16, 17. Okay, 22. Yep, I simply didn't count it right. 2, 4, 10, 13. 1 plus 3 is 4, 5, 6. Alright, we eventually got there. So this was a 2. Yep. You do math often enough, you'll have more mistakes than successes. Even though you're striving for more successes. Sorry. Alright, so as the general idea of addition, questions, comments, concerns? Anything else? So, where we have addition, we also have subtraction, and that is the taking away of 2 bits, or 2 things. Excuse me. Oh, I see my camera's overheating, that's why it's all blurry. Well, this is odd. Poor thing. This might be an inhibiting factor. Oh, okay, never mind. Ho-ho. Poor camera. It's trying so hard. So subtraction, sorry, where we have addition, which brings things together, subtraction takes things apart. That seems pretty intuitive. So here, arguably this looks like 12 minus 5, or 31 minus 29, or so on and so forth, each of which is 12 items minus 5 of those items. The remaining items is 7. 31 minus 29 ought to be the remaining bits. The way to check your answer, especially with subtraction, is addition, because they're complementary functions. They complement each other very well. So 5 and 7 equals 12, and 29 plus 2 equals 31. So where you can get here, you can also get back to where you came. So a great example of bigger numbers doing bigger things. 3, 4, 6, 8. 2, 4, 8. Now, I'm going to go ahead and try this from right to left. before trying it from left to right. So 8 minus 8, that's 0. As 8 minus 8, there's nothing left. 6 and 4 is 2. 4 and 2 is 2. 3 and 2 is 1. So it ought to be the same doing it from left to right. 3 and 2 is 1. Excuse me. 4 and 2 is 2. 6 and 4 is 2. 8 and 8 is 0. So it came out to be the same. And whereas addition had the phrasing such as add increased by the sum of, so such as which subtract could be decreased by, less than, or the difference of. So we get the difference of 12 and 5. In this particular case, when it says the difference of this and that, the first number subtracts this number. So it'll always be this minus that. This minus that. To be 12 minus 5, as we have seen, is a lovely 7. Or we could have 20 decreased by 8. So 20 minus 8, 12, and the like. Now, as we had just gone over with carrying for addition in a tedious manner done several times, where we have carrying for addition, we have borrowing for subtraction. So another example thereof, as far as borrowing, is 52 subtract 27. So because the 2 is smaller than 7, we have to borrow from the 5 to make that something bigger. So a 12 ends up being bigger than 7. And that 5, since we borrowed from it, becomes less than what it was. 1 less means 4. So 12 minus 7 is 5, and 4 minus 2 is 2. Left to right, 5, 2, 2, 7. 5 minus 2 is 3, but you can't do anything here, so you still need to borrow no matter which way you've gone. So that becomes 1 less. So it would be 12 minus 7 is 5. Notice how going from right to left and left to right, where we have borrowed from is different. And that's just a personal notation. You could have simply gone back up here and re-evaluated it to be 2. Potato, tomato, left and right, you still need to borrow. And where you borrow from is just a matter of where you write where you've gotten it from. Yeah. Sure. And to put it simplistically, let's say we have another example, and we'll break this out in a lot more detail. So we have 32 minus 17. Inches to the y. So 32 is 30 plus 2. 17 is 10 plus 7. So that you get a regrouping, as it were, borrowing or regrouping. So then you get 20 plus 12 minus 10 plus 7. Because you've taken a 10 over from over here and put it over there. So 12 and 7, that's 5. And 20 minus 10 is 10. And you put that back together and you get 15. Et voila. Sure. Okay. Thank you. I appreciate that. Okay. moving on. Share. And to always check your answer. I'm sorry. So you get, let me see, from our previous example, we get 25 plus 27. That's 42, 52. And then we get 17 plus 15 is 1, 2, 2, 3, so 32. Just to make sure we've covered our bases. All right. To do one more with borrowing all the paper. So another example, if I may. Minus 2, 3, 6, 5. Left to right. Here we go. So 4 and 2 is 2. 0 and 3, so that'd just be 1. So 10 minus 3 is 7. To which case we have 5 minus 6. 15 minus 6 is 9. And 3 minus 5, so that's 8. 13 minus 5 is 8. So that should be 1, 6, 8, 8. And going from right to left, we get the 3, we need to borrow 5 and 4. 13 is 8. 4, we borrow. Sorry, we can't borrow from a 0, so you'd have to come all the way over here to get a 4, turn it into a 3, you get a 10, and you borrow from that, so that's a 9. So now you have a 14 minus 6 is 8, and that 9 minus 3 is 6, and that 3 minus 2 is 1. Yes, and you indeed can double borrow, because if there's nothing there, you have to make it bigger, and then borrow from the bigger. And to check our lovely answer, we have 1688. 2, 3, 6, 5. 8 and 5 is 13. 1 plus 8 is 9. Plus 6 is 15. 1 plus 6 is 7. 10. 1, 2, 3, 4. I would do this from left to right, but I think you get the gist of where what goes. Questions, comments, concerns. I think we're doing fairly decent. Sorry, getting there. Now, I would like to make a comment that throughout this projection of this episode, what I'm seeing on my screen is reverse of what you're probably seeing on your screen, so it's a little confusing to see what you're seeing and verifying that it's right. It's just kind of funny that way. So I get the gist that it's coming out, or else someone would have said something. Right. Now we get the gist of adding and subtracting, putting together and taking apart of numbers and their values. Rounding, estimation, and order, very important. And this mostly has to do with the mental visualization of a number line. So if you have two values, let's say 8 and 12, and you're given the number 10, to estimate, if you have to say that this number is closer to 8 or 12, you wouldn't be able to say so because it's right there in the middle, because it's 2 units from each. It's right there in the middle. But if it was an 11, it would be closer to 12. You would estimate it closer to 12. Or if it was a 9, you would estimate it closer to 8. The reason why this is important is because sometimes we simply write numbers in their nearest thousandths, hundredths, tens place as needed, because understanding that you pay, let's say, a bill closer to the tens versus the ones is more important to kind of get an estimate of what you're dealing with. You don't have to look at every single digit in every single place. So, using an example, so we have this particular number, 2, 3, 7, 8, and let's round it to the nearest hundreds place. So we don't really need to bother with this when we're doing the hundreds place. We look at these and kind of tell if we need to go up or down with our estimation. Generally, going forward, if the digit is 5 or more in the very next place behind where we're trying to estimate, that digit and all its digits to the right still become 0. And this digit will increase in value. So this will be closer to 4 because this 7 is greater than 5. We will round up to 2400. So on your mental number line, where we have 2, 3, 7, 8, it would be closer to 240 than it would be 230. Because arguably you are 78 steps away from 230 and you are 22 steps away over here. Just because the difference between 240 and 230, the difference of me subtraction, is 100. And then the difference between 240 and 2, 3, 7, 8, because you need to borrow if you're going from left to right, or going from right to left. Either way, you need to borrow. If you're going from right to left, you need to borrow twice. So then you have 4, 3, so that would end up being a 9 if you carry the 1. So there would be 2, 2, 3, 0, so 22 units. And then 2, 3, 7, 8 minus 23. This one's pretty simple because the 7 and 8 dropping the 23 cancel out. And so we know that 78 is bigger than 22, therefore it is closer on this side. I know that was quick and kind of thick, and comparing numbers as to what's greater and less is more or less like, this is where the art of feeling comes into math. Is like, do you feel better with $78 or $22? Because, I mean, 78's bigger, you can do more with it. So you may feel better with it. Here. What I've personally done with estimation in my life and the everyday basis is when I go grocery shopping and I don't have a list, but I have a general budget. Let's say I have a budget of $80. I have $80 in cash on my person. I have no backup way of paying, so everything I have to pay for altogether has to be less than $80. I go and get some spaghetti, which is $3.75. And then I go get the sauce, which is $6.25. So noodles, sauce, all sorts of stuff. So you get this wonderful list of just groceries that you have to pay for. Now, what I've done in estimating, and because it's in a grocery budget, it'd do you better. Man, we just went back on a rule we just said. In groceries, you'll always want to round up. So you'll always have that difference as padding. So $3.75, you round that to 4. $6.25, you'd still round that to 7. $11.88, that'd be 12. $5.33 would be 6. And $7.99 would be 8. Now, you could get away with rounding down, but it's less reliable, especially when you have a budget to work with. And now that we have nice round numbers to work with, we can add that up to make sure it stays under the $80 per budget. So 4 and 7 is 11. 11 and 12 is 23. 23 and 6 is 29. So that's 37. And 37 fits in our $80 budget. And this does not include any taxes, which is a weird thing that you have to also add into to estimate. That's an entirely different critter. But alas, this is my general rule for making sure that a grocery run stays under budget. Generally. Other than writing a grocery list to go. And just because I have used the notation something to express when a number is greater than. So let's say, because we know 85 is greater than 40, we have the greater than sign between the two. Greater than, which a lot of I've seen of this, it's an alligator's mouth that eats the bigger number. That's always how I've seen it. So greater than means the first number is bigger than the second number. Less than, using the same numbers because continuity, we know that the alligator's mouth will still want to eat the bigger number, so it'll face the bigger number, where 40 is less than 85. It has to do with the order that it's read, whether or not it's called greater or less than. The sign will always go to the bigger number. So we have examples such as, if I may, 7 and 10, 25, 20, 200, 308, and 0. So because 10 is bigger, we'll go that way. 25 is bigger, we'll go that way. 300 is bigger, and we go that way. And 8 is bigger than 0, we go that way. So we would read this as 7 is less than 10. 25 is greater than 20. 20 is less than 300. And 8 is greater than 0. So we'd say this one's less than, greater than, less than, excuse me, and greater than. And that pretty much rounds out rounding and estimation. Questions, comments, concerns? So, next we have, and I think this is kind of my favorite operation in all of mathematics because you can do so much with it, is multiplication. So the multiplication is just the series of, let me get this way, the series of adding. This is odd to me. How'd you do that? I'm going to move that a little bit there. There we go. So if we see something in multiplication, such as 4 times 5, that is saying we are adding 4 5 times 5, or we're adding 5 4 times. Whichever is really easiest to think about. So 4 and 4 is 8. 8 and 8 is 16. 16 and 4 is 20. 5 and 5 is 10. 5 and 5 is 10. 10 and 10 is 20. Yep. Sorry. For clarification, this particular symbol is called multiplying. So you can have 4 times 5, or there are other symbols. You can have 4 times 5, or if you put 4 parentheses 5, these all mean to multiply. Symbology is pretty cool with math. You can get whatever you need and however you need it to look like. So, a lot of examples. We have 3 times 3, which can be done either way. 3 plus 3 plus 3, or 3 plus 3 plus 3. 3 and 3 is 6, and 6 and 3 is 9. 9. Another way to see this visually is you get 3 by times 3. So you get 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Is that pretty good? Another thing about math, very similar to addition, is that it is also a commutative property. So that means we have Now remember, commutative has to do with the order in which it is labeled. So generally, A times B equals B times A. Multiplication, it doesn't really matter. So what that means, so let's say we have 3 times 2. It should equal 2 times 3. So 3 times 2 is 2 plus 2 plus 2, or 3 plus 3, which equals 6. And 2 times 3 is 2 plus 2 plus 2, or 3 plus 3, which still equals 6. So. Oh yes. So multiplication is one of those lovely and funny things. There's another rule. I think we may have passed a previous one. We'll come back to that. There's another rule called the distributive property. Of multiplication over addition. And I believe I'll get through this topic and we will have to wrap up because it's already 7 o'clock here. Dang, math takes a long time, dude. So, that is to say, if we have some number multiplied by a sum of 2 or more options, that is to say we can multiply each of these options. Oops. Excuse me. By the sum. Because, and I will show you by example, let's say we have 3 times 5 plus 2. So that means we can rewrite it as 3 times 5 plus 3 times 2. So if you will to do it this way first, so 5 plus 2 is 7. So 3 times 7, and 3 times 7 is 21, believe it or not. Or if you were to do it this way, 3 times 5 is 15, plus 3 times 2 is 6, and 15 plus 6 is 21. And this particularly has to do with the order into which it's done. You do multiplication before you do addition, except when there are parentheses involved. We will go into detail more about the why of that later. Put an asterisk here because it means a lot to understand why the order is important for you to understand completely the distributive property of multiplication over addition. So one last example before we cut out today over multiplication. Similar to addition, we also have the carry. Not the carry, just the carry. So let's say we have 25 times 3, and you can have 25 times 3. Either notation represents the same function. This one is just easier to manipulate in a lot of cases. So when multiplying, we usually use the bottom number to work with the top number. So we start with 3 times 5, and that is 15. So that is the 1, we carry the 1. Now we don't add that just yet, we multiply first. So 3 times 2 is 6, plus 1 is 7. Et voila. Or, if need be, if you do it from left to right, you get, and the 2's in the tens place, so keep that in mind. 3 times 2 is 60 in the tens place. You put the addition there, because the addition won't happen up here, it'll happen down here. So 3 and 5 is 15. Add the 2, so that's 75. Peace. So, given the time for brevity, we'll go over the order of operations for the distributive property of multiplication over addition next time, and then we will move on to geometric applications thereof going forward. It kind of gives a context as to why knowing this and working with this is so important and how it can be important to you in any big or small way. I appreciate all the support. Thank you. Alrighty, I will see you Thursday, 6 p.m. to pick up where we are. Bye.